Last year in Physics 20, we learned about a law called Newton's Law of Universal Gravitation. It wasn't one of Newton's three laws, but it was pretty important. It said that any two objects with mass will, will exert a gravitational force of attraction on each other. That's the Earth and the Sun are attracted to each other because of gravity, and you and the person sitting next to you are attracted by a force of gravity. Any two objects with mass are attracted by gravity. Gravity is an important everyday force, okay, we experience every single day. There's another force that we experience every day as well, though we might not necessarily notice it quite so much or realize that we're experiencing it quite so much, and that's the electrostatic force. Last year, we learned to calculate the force of gravity. We found that it was F is equal to G m1 m2 over r squared. Today, we're going to learn to find the force of electricity, or the electrostatic force that either attracts two objects together or repels two objects away from each other. Again, another force that we experience every single day, we just may not realize we experience it every single day. Well, in order to derive this equation or figure out this equation that describes the electric force of attraction or repulsion, I'm going to tell you about an experiment that was performed by a guy named Charles Augustin de Coulomb. This is a bit of a simplification of it, but it's a pretty good explanation of it. This is a top of a box or the top of a cylinder or the ceiling of a room. Doesn't really matter what it is. Something that I can connect a string to, a thin string. On the end of the thin string is a rod. And on either end of the rod is a mass. They're going to both be the same so that this thing is symmetrical and doesn't tip over. But really what I'm concerned about is only one of them. We're going to charge one of them. We're going to call it Q1. So it's going to have a certain number of coulombs on it. Maybe we rubbed something against it, charging by friction, whatever. It's got a charge, Q1. I'm going to bring another charge nearby. We're going to call it Q2. Q1 is now close to Q2, and as a result of that proximity and the charges on Q1 and Q2, these guys are either going to attract or repel each other. If they're both the same charge, they're going to repel each other. If they're opposite charges, then they're going to attract. It doesn't really matter what happens here. There's going to be a force, either of attraction or repulsion. What we want to do is measure that force. We want to measure the force. We also want to measure charge 1. We also want to measure charge 2, and we also want to measure R, that is the distance that separates those two charges. R is the easiest one to measure here, because we can simply use a ruler or something like a ruler to measure the distance that separates these charges. Q1 and Q2 are a little bit harder. In fact, Coulomb, when he performed this experiment, couldn't actually measure the exact values of Q1 and Q2. Rather, he could only measure the relative values. Here's how he did it. Let's say he's trying to manipulate the value of Q1. He's got a value of charge 1 that he calls Q. How many coulombs is it? Don't know. It's Q. If he touches that against something that's neutral, then it becomes a half Q. And then if he touches it against something that's neutral again, it becomes a quarter Q, and so on. So he can actually change the value of Q1 and Q2 for that matter simply by touching them against neutral objects and repeatedly cutting the value of the charge in half. So he doesn't know what the charges are, but he does know what he's changing them by. So I'm going to put check marks by this. Even though we don't know what the value is in coulombs, we know what the relative value is, what it is compared to what it was. Force, that's an icky one for this. How do we measure the force for such a small force here? Well, you guys have been to playgrounds and been on swing sets, right? Inevitably, especially when you're little, you swing it on the swing set, and then you decide you're going to twist that swing set around. You sit on it, right, and you twist it around. You guys know that when you twist that swing set around, the more you twist it, the harder it is to twist, right? The more force is required to twist it. We could measure the force required to twist that swing set. You could do that. You could do an experiment at the playground to measure how much force is required to twist it, a quarter of a turn, a half a turn, 3/4 of a turn. I wouldn't suggest you do that, because if you go to a playground with all kinds of physics equipment to measure the force on a swing set, you might get beat up. But you could, if you really wanted to, measure the force that was required to twist at a certain amount. Coulomb would have did a similar experiment with this string. So he would have known that when I bring Q2 nearby Q1 and it twists 37 degrees, he would have known how much force was required to do that. So he's using the amount of twisting as a measurement of the force. Now, he's going to perform 3 experiments here in order to figure out what the relationship between all these variables is. In the first experiment, he's going to manipulate the value of Q1. He's going to change Q1 for, I don't know how many trials he would have done. 10 trials, 20 trials, 50 trials, I don't know. He's going to manipulate the value of Q1. He's going to see how the force responds. The electric force of attraction and repulsion is going to change because Q1 changes, but how much is it going to change by? That's what we want to see here. If this was an experiment that you guys were handing in, I would expect you to give me 2 really important control variables. What do you think they'd be? What would I have to keep the same here? Lots of things that I should keep the same, but what 2 things must I keep the same in this experiment? Yeah? Yeah, we got to keep Q2 and the value of R constant. So when Coulomb performs this experiment, he plots a graph. He manipulated the value of Q1 and he saw how F responded to that. Responding variable always goes on the y-axis. When he did this, he would have found that the relationship between F and Q1 was a linear relationship. In other words, F is directly related to Q1. That symbol just means proportional to. As Q1 goes up, F goes up. As Q1 goes down, F goes down. If Q1 is tripled, F gets tripled. It's a linear relationship. Well, then he would have performed another experiment. This time, his manipulated value would be Q2. And his responding variable would be F again. His control variables would be, what does he got to keep the same in this one? Somebody said it? He's got to keep Q1 and R the same. So now this time he plots a graph of F versus Q2. How does the value of Q2 affect the value of the force? Well, in the same way as Q1 does. It's a linear relationship. So as Q2 goes up, F goes up, whereas Q2 goes down, F goes down. Finally, his third and final experiment, he's going to manipulate the value of R. He's going to change the separation distance between the 2 charges. He's going to see how the force responds to that. As I make R bigger or smaller, does F get bigger or smaller? What would be my control variables here? What would I have to keep the same? You guys know this. Q1 and Q2. Couldn't change the values of those because I want to see how R affects F, not how Q1 and Q2 affects F. I already know that. This time I'm going to plot a graph of responding versus manipulated. But this time the graph is going to take a completely different shape. It's going to look like this. This shape tells us that F is not linearly related to R. In fact, it tells us that it's inversely related to R. Not just inversely, but inversely related to the square of R. As R goes up, F goes down exponentially. And that should make some intuitive sense to us. As if you're trying to measure the force between 2 charges, the closer they get to each other, the bigger the force is going to be. Right? You get more effect when they're close to each other. So Coulomb puts all this together. He's got three relationships now, right? He knows the relationship between F and Q1, F and Q2, and F and R. He puts them together. If F is directly related to Q1 and Q2 and the inverse of the square of the distance, then the relationship looks something like this. But that's not an equation. To get an equation, we have to replace this proportionality sign with a constant. And it becomes this, K times Q1, Q2 over R squared. F, the force of attraction or repulsion, is equal to K, a constant, times the value of Q1 and Q2 over R squared. Does this look at all familiar to you guys? Like, does this remind you of anything that you did in Physics 20? Yeah. 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 The equation for gravity, Newton's law of universal gravitation, was G m1 m2 over R squared. Does anybody remember what the value of G was? If you don't, that's okay, because I probably wouldn't have. It's on your data sheet. It's 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Here, the value of K, the constant, is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. These two relationships have a lot in common, but also some things that they don't have in common. Firstly, what do they have in common? The structure of the equation. We call them both inverse square relationships, because the force is inversely related to the square of the distance in both cases. They're both inverse square relationships. What makes these things different from one another, these two equations or these two relationships? Well, clearly, charge versus mass. Although the structure of the equation is the same, the variables aren't. We're using charge instead of mass. Gravity is always attractive, right? You ever see gravity repelling anything, pushing anything away? Gravity is always an attractive force, but the electric force can be attractive or repulsive, so the direction can be different. And what else is different? The magnitude. Think about your everyday life and your everyday experiences. Which force do you think is a bigger force? Gravity or the electric force? Which force do you think is bigger? I'd like to get one person on each side so we can kind of debate this a little bit. Joshua, what do you think?
I think that gravity has the most influence on
Okay. Okay. So Joshua says that gravity has the biggest influence on us. Do you disagree with that? Okay. You're going to say the electric force has a bigger influence on us? Okay. How many people agree with Joshua that gravity has a bigger influence on us in our everyday lives? Okay, a few hands going up. How many people think agree with Matt and say the electric force has a bigger influence? Okay, it's about 50-50. Okay, not bad actually. Everybody in the other class went with gravity. Everybody went with gravity in period one. Well, let's, well, for some things, I guess, but I guess if you fall in love with somebody, you have to be attracted, right? So I guess maybe. I'm standing on top of a desk right now. I'm going to jump off the desk. Okay, what pulls me down from the desk? Gravity, right? Pulls me down quite a bit, right? Quite hard, right? It caused me to accelerate at 9.81 meters per second squared. We got snow this morning, a few inches of snow this morning. I grew up in Nova Scotia where you get 50 centimeters 60 centimeters. It was nothing to get 50 centimeters of snow when I was growing up. Sometimes we got 100 centimeters of snow when I was growing up. It was great because we'd have school canceled 5, 6, 7, 8, 9, 10 times a winter. It was great, no school. In my 12, 13 years of school, I bet I had school canceled 75 times. Sometimes when we get that big dump of snow, that 50 centimeters of snow, sometimes my friends and I would go up and hang out at my elementary school. Why would we go to school in those days? Because my elementary school was a 3-story school. The first floor was half basement and half above ground. And then there was the second story, and then there was the third story. And the third story had these wooden stairs, these big wooden stairs going up, so that at the end of recess, kids would line up at the bottom of the stairs and then go up directly to the third floor to their classrooms. And on days where you get tons of snow and wind, the snow would drift against these wooden stairs. So not only would you get 40 or 50 centimeters of snow out in the middle of the field, but you'd also get this drifting. So sometimes the snow pile was a meter or 2 deep. So we'd climb up these stairs on these snow days up to the third floor, and then we'd jump off into the snow drifts. And we'd accelerate downward at 9.81 meters per second squared every single time. Guess what else happened every single time? We stopped. Every single time we stopped. We never went through the ground and kept going. Every single time we stopped. Did that change anybody's answer?
Electric, the electric force can go through objects.
Okay, it can. Yeah, it can, but that's still not going to change your answer. Go ahead, Kevin. Attraction versus repulsive there. Yeah, that's just attraction versus repulsive. Here's what happens. Gravity pulls me down at 9.81 meters per second squared. It's going to be a pretty big force, right, to pull me down at 9.81 meters per second squared. But what stops me? What stops me? Physics 20, you learned the force of the ground pushing up is called the normal force. But what is the normal force, really? What is it? Well, it's actually a force of repulsion between electrons in your atoms and electrons of the atoms in the ground. We know that the force of attraction or repulsion electrically is inversely related to the square of the distance. So as I get ridiculously close to the ground, when I get on the ground and I start compressing my feet and start compressing the ground, then electrons in my body get really, really close to electrons and atoms in the ground, and they start repelling each other. And eventually, that causes me to stop. So what's a bigger force now? The force that got me to the ground, or the force that overtakes that force that got me to the ground and stopped me? The electric force is a bigger force. Okay? And in most circumstances, not in every case, but in most circumstances, the electric force is a bigger force. Okay? There's 4 fundamental forces of nature. Gravity is one of them. The electromagnetic force, of which this is part, is another one. Then there's 2 more forces in the nucleus called the strong nuclear force and the weak nuclear force. Strong nuclear force we've actually talked about a little bit. The weak nuclear force we haven't. Gravity is the weakest of those 4. Gravity is a really weak force, actually, compared to other forces. We just perceive it as big because that's the one that we notice every day. But if we actually took note of, look, I'm walking on the ground right now. What's keeping me from falling down into the ground? An electrostatic repulsive force. If we took note of that, then we realize, well, wait a sec, gravity is not so big after all. That repulsive force has to be bigger. That's Coulombs Law. I got a chart for you here to copy down. That's going to be the last thing for today here, okay? Just a comparison of Coulombs Law, which is that F is equal to KQ1, Q2 over R squared, versus Newton's law of universal gravitation, which is the whole thing you learned in physics 20, GM1, M2 over R squared. They're both inverse square relationships. which means that F is related to the inverse of the square of the distance. That's what they have in common. The magnitude? Well, we said normally Coulomb's law would be a bigger force. And if we think about our experiences every day, that makes sense to us, right? But look at the constants as well. K is 10 to the positive 9. G is 10 to the minus 11. K is 10 to the 20 times bigger than G. So we can tell just by looking at the constant that the electric force is going to be a bigger force. And finally, the direction. Well, the Coulomb's law force, the electric force, could be attractive or repulsive. We get repelled by the earth, by the ground, when we get really, really close to it. The balloon gets attracted to the wall. Gravity is always attractive. I've never seen gravity repelling anything. I've seen it attracting lots.